Intelligence is not the ability to store information, but to know where to find it.
That quote from Albert Einstein?
Yeah, it sits right at the top of the research we're covering today. It frames the discussion perfectly because we are looking at a paper that it fundamentally questions how artificial intelligence handles memory.
It is a really fitting opening. We're doing a deep dive into a paper titled General Agentic Memory via Deep Research.
And this comes from a collaboration between the Beijing Academy of Artificial Intelligence, Renmin University, Peking University, and Hong Kong Polytechnic University.
Right. They're proposing a framework called General Agentic Memory, or GAM.
Before we really get into GAM, we need to address the elephant in the room for everyone listening. The current trend in AI is just to make the context window bigger.
Huge windows.
Yeah. We have models now that can take in hundreds of thousands of tokens. If a model can just read an entire book in the prompt, what do you even need a complex memory system?
That is the common assumption. The belief is that if you fit all that data into the window, the model just understands it. However, the researchers identify a phenomenon they call context rot.
Context rot? That sounds like a data hygiene problem.
It effectively is. The paper points out that while long LLMs, those models with massive context windows, they can technically accept the input,
Sure.
but their performance degrades significantly when that input is full of noise or distracting information.
I see.
Just because the data is sitting there in the prompt doesn't mean the model can effectively reason across it.
Dumping a year's worth of logs into a chat window might result in the model technically reading it.
But completely failing to answer a specific question about a bug from 6 months ago.
Right.
The prevailing method to handle this until now has been ahead-of-time compilation, or AOT.
Ahead of time.
This is how most memory systems function right now. They take the raw context, that massive stream of daily data, and they compress it into a lightweight memory structure before the user even asks a question.
They are basically trying to predict what is going to be important later.
They are summarizing, and the paper identifies a critical flaw here. Compression inevitably leads to information loss.
Because it's a static structure.
Yes. If you compress a sprawling conversation into a neat little summary, you lose the specific phrasing. You lose the timestamps or those minor variables that just didn't seem important at the time the summary was made.
But then weeks later, you might ask a question that hinges on that specific minor variable.
And the AOT system fails. That detail was smoothed out during compression. It lacks the fidelity to answer ad hoc, nuanced requests.
Which brings us to their solution. GAM proposes a massive shift to just-in-time compilation, JIT.
The shift is from preparation to reaction. Instead of trying to build a perfect, compressed memory bank beforehand, GAM keeps the offline memory relatively simple. It performs the heavy computational lifting, the actual act of remembering, only at runtime, when the request actually comes in from the user.
It waits until it knows what you want before it decides what is important from the past.
That is the core philosophy. To achieve this, they developed a dual design architecture. The system is split into two distinct components, the memorizer and the researcher.
Let's start with the memorizer. This operates in the background.
Yes, this is the offline stage. The memorizer processes the agent's history as a stream of sessions. Its goal is to preserve information without burning through computational resources on deep analysis that might never be used.
It just watches and logs.
It performs two very specific operations.
The first one is memorizing.
Memorizing produces what the paper calls a memo, denoted in the paper as MUI. Think of this as a concise snapshot of a new session.
Like a high-level tag.
It updates incrementally. It captures the high-level events. Things like user asked for Python code or system debugged a database error.
Wait, that sounds a lot like the summaries we just criticized in the anytime systems.
If that were the only component, it absolutely would be. But the memorizer also performs a second operation, paging. This is the safeguard. While the memo provides the quick overview, the paging process maintains the complete historical information in a page store.
We have the summaries for scanning speed, but we keep the raw data for accuracy.
We keep the raw data. But we don't just dump it in a disorganized pile. The memorizer generates a header for each session. The paper describes this as decorating the session.
Decorating it with what?
Context. The header contains information from the preceding trajectory. It stamps the raw data with the context of what was happening leading up to that moment.
Which aligns with the principles of contextual retrieval.
Yes. That distinction really matters. If you have a raw log entry that just says error 404 and you look at it a year later, you have no idea what caused it or what you were doing.
Right.
But if the header says, during user attempt to access admin panel via API v2, now that raw data has immediate meaning,
You have preserved the semantic meaning.
by attaching that context, the system ensures that if a page is retrieved hundreds of turns later, it is not just an isolated fragment of text, it carries its own history with it.
The memorizer builds this two-tier library: lightweight memos for scanning and context-rich raw pages for deep reading.
Correct.
Now, let's say I am the user. I ask a question. This triggers the second component, the researcher.
This is the online stage, and it is where the just-in-time principle actually applies. The researcher does not simply look up an answer in a database.
Right.
It constructs a custom answer context from scratch. The paper calls this process deep research.
It sounds highly active. It's not just retrieving, it's working.
It starts with planning. The system uses chain of thought reasoning. It looks at your request, and it looks at those lightweight memos the memorizer built. It tries to determine its information needs.
It figures out what it doesn't know.
It creates a search plan. It might decide, I need to find the specific error code from last Tuesday, and then I need to find the solution we applied on Wednesday.
To execute that plan, the paper specifies a toolkit. I noticed it highlights 3 specific tools. Why does it need 3 different ways to search the page store?
Because different types of information require different retrieval strategies. You can't use one tool for everything. The first tool is an embedding model.
For vector or semantic search?
Yes. This is for finding concepts, even if the words aren't identical.
If you search for database issues, the embedding model can find logs about SQL injection or connection timeouts because they are semantically related in vector space.
But sometimes that semantic space is too fuzzy.
Right.
That is why the second tool is a BM25 retriever. This is a strict keyword-based search algorithm. It is crucial for finding specific names, ID numbers, or unique terms.
If you need to find a variable named extemp5.
Vector search will struggle with that, but BM25 will find that exact string immediately.
And the third tool?
An ID-based retriever. This allows for direct page exploration.
How does that work in practice?
If the researcher's planning phase identifies a specific session ID or page number from the memos, for example, it reads the memo and says, refer to session 105, this tool lets it pull that specific page directly. No searching required.
It has a plan, and it has the 3 tools. It goes out and retrieves the relevant pages from the page store.
Yes.
In a standard memory system, this is where it would stop. You would just feed those retrieved pages to the LLM and hope for the best.
Jam is a massive step further. The researcher moves to a reflection stage.
This seems to be the critical differentiator of the whole paper.
It is a built-in quality control loop. The system asks itself a binary question. Is the information I have retrieved accurate and complete enough to answer the user's request?
It grades its own homework before handing it in.
If the answer is no, it generates a new request. The paper labels this R prime, and it loops back to the search phase.
It iterates.
It might realize, I found the error log, but I didn't find the solution we implemented. So it generates an R prime specifically asking for this solution and searches again.
It continues this loop until it is satisfied.
Until the internal answer is yes, or until it hits a predefined limit to prevent an infinite loop.
That makes sense.
Only then does it proceed to integration, where it synthesizes all the retrieved pages into an optimized context, known as C star. And that is what is used to generate the final answer for the user.
This process of planning, searching, and reflecting it heavily mimics how a human researcher works.
Very much so.
You don't just grab the first book off the library shelf. You open it, you check if it actually answers your specific question, and if it doesn't, you go back to the catalog.
The paper emphasizes that this isn't just a static heuristic they hard-coded. The system is capable of end-to-end optimization. They used reinforcement learning to train these components.
How do you apply reinforcement learning to memory retrieval? That's usually for game playing or robotics.
You use a reward function, gamma. It is based on the quality of the final generated answer. Both the memorizer and the researcher are trained via policy gradients.
The system gets points if it constructs a good context that leads to a correct answer.
And it gets penalized if it fails. Over time, the researcher learns which of those 3 tools work best for which types of questions.
It learns when to stop searching and when to dig deeper.
It is constantly optimizing its research strategy based on successful task completion. It's a learning memory system, not just a storage drive.
Let's move to the evidence. Theory is great, but how does GAM actually perform when you put it to the test?
The researchers compared it against a really wide range of baselines.
They looked at memory-free methods first, right? Like the long LLM approach we discussed earlier and standard RAG, retrieval augmented generation.
Yes. They also compared it against state-of-the-art memory-based methods, things like MEM0, MemoryOS, and AMEM.
We touched on context right at the beginning. Did the benchmarks actually back that concept up?
The benchmarks confirmed it clearly. The paper notes that long LLMs performed well under expectation on benchmarks like Hotpot QA 56K and Narrative QA.
Even with massive context windows.
Even with 128K token windows. When faced with massive amounts of distracting information, the brute force approach of just dumping everything into a large context window degraded performance.
In contrast, how did GAM handle the really complex tasks?
The most revealing results came from the ruler benchmark, specifically a task called multi-hop tracing.
Multi-hop implies connecting the dots across different pieces of information.
The task requires the system to track variable values across multiple steps of assignment buried in a long text.
Can you give an example of that?
Sure. Something like variable A equals 5. Later on, variable B equals variable A plus 2. Even later, variable C equals variable B times 3. The system has to trace that logic backward through a massive context to find the final value of C.
That requires holding a thread of logic while ignoring thousands of words of noise.
GAM achieved over 90% accuracy on these multi-hop tasks.
90%. That is a very high bar for that kind of reasoning.
Yeah.
How did the competitors do?
The contrast is incredibly stark. In some settings on this specific metric, the RAG baseline scored 0.00.
Zero.
Complete failure.
Why did RAG fail so completely on a tracing task?
RAG relies almost entirely on semantic similarity. If the user's question is, what is the value of variable C, Argy might successfully retrieve the sentence defining variable C.
Because the keywords match.
Right. But it likely fails to retrieve the sentence defining variable A because variable A doesn't look semantically similar to the prompt about variable C.
It misses the intermediate steps entirely.
It finds the last piece of the puzzle but loses the rest of the picture.
Because standard RAG doesn't think or plan. It just matches text patterns.
GAM, on the other hand, with its iterative reflection, retrieves C. Then it realizes, I found C, but C depends on B. Now I need to generate a new search specifically for B. It traces the hop.
The paper also includes ablation studies. They broke the system down piece by piece to see what was actually driving this high performance.
They tested the tool synergy first. They found that combining the embedding, BM25, and Page ID tools yielded the absolute best results. Using any single tool in isolation caused massive performance drops.
Which confirms your earlier point about different data needing different search methods. You need the full toolkit.
They also tested the reflection depth. They wanted to know how many times the system actually needs to loop back and check its own work.
Is there a point of diminishing returns there? You wouldn't want it looping 20 times.
There is a clear limit. Increasing the reflection depth from 1 to 5 consistently improved the F1 score, which is their metric for accuracy. But the gains started to diminish significantly after depth 3.
Checking your work 3 times seems to be the sweet spot for efficiency versus accuracy.
They also looked at retrieval volume, how many pages the researcher pulls from the store during its search phase.
Did more pages equal better answers?
Increasing the number of retrieved pages from 3 to 20 boosted performance across the board. This confirms that the deep research concept pays off. The more thorough the search through the page store, the better the final optimized context.
We do have to talk about the cost, though. This sounds incredibly expensive in terms of time. Planning, searching, evaluating, looping back.
It takes longer than a millisecond database query. There is no getting around that. The efficiency analysis in the paper shows that GAM is slower than simple AG.
But how does it compare to the other advanced memory systems, the ones trying to do AOT compression?
Its time cost is actually comparable to systems like MEM0 and MemoryOS. The offline build time, the background work the memorizer does to create memos and headers, grows linearly with the context length. It is highly manageable.
The researchers argue this is a necessary trade-off between speed and quality.
That is their central argument. They contend that GAM offers the best overall cost effectiveness. You pay a slightly higher time cost at runtime compared to a simple RAG, but the return is a substantially higher answer quality.
If the fast system gives you an answer in 0.1 seconds, but the answer is completely wrong, like that 0 score on Ruler, then the speed is totally irrelevant.
Especially for autonomous agents. If you have an AI agent performing complex tasks for you, booking flights, managing code repositories, handling financial data, accuracy is paramount.
You are more than willing to wait 10 seconds for a correct, deeply researched answer rather than getting an instant hallucination.
This brings us back to the core concept of the paper. It seems the just-in-time approach is really validating Einstein's view from the beginning of our discussion.
It effectively decouples the storage of history from the understanding of it.
In ahead-of-time systems, you try to understand the history at the exact moment you store it, which limits you because you don't know the future context.
In JAM, the history is stored raw, but decorated.
The understanding is constructed on demand, specifically tailored to the exact question you are asking today.
It fundamentally changes the role of the AI agent. It is no longer just a librarian handing you a pre-written summary book. It is an active researcher writing a custom report for you.
A researcher that verifies its own sources before it hands you the report. The shift from storing to searching and reflecting allows large language models to handle massive, rapidly expanding contexts.
Without losing those fine-grained details necessary for complex tasks.
It solves the scale problem by ignoring most of the data until it actually matters.
And by ensuring that when it does matter, the system has the sophisticated tools to find it.
That sums it up.
This general agentic memory framework really seems to set a new standard for how we should think about long-term coherence in AI. It is not about building a bigger brain with a bigger context window. It is about developing better study habits.
That is a perfect way to phrase it.
But it does leave you wondering, if AI systems become capable of doing this kind of deep recursive research on their own histories, at what point does the raw page store become so impossibly massive that even the researcher's planning phase takes too long? We might eventually need a memory system just to manage the memory system.
It's a fascinating problem for the next generation of papers.
That wraps up our deep dive into general agentic memory via deeper research. We will catch you on the next one.